Hello students, welcome to the lecture that's going to be about climate models. We've already talked about numerical weather prediction and how we use numerical models of the atmosphere to make forecasts about weather, and how that all works with regard to like the 7 primitive equations and the like time steps and all that kind of good stuff here. We're going to learn about that in a little bit more detail. Before we move on though, I just wanted to show you real quick all the pictures that are in the backgrounds on these this presentation were given to me by, his name is Patrick Ahern, and he was actually Creighton's very first environmental science major. And I thought I'd kind of, since we're in Environmental Sciences 105, I thought I'd give it to you. He was recently with his work actually in Patagonia, and I got a chance to talk to him, and so I've got some pictures from Patagonia going on in the background. Environmental sciences is a cool discipline with lots of very interesting career fields, and you know, consider taking more environmental science or atmospheric science courses in the future. Alright, now we started learning about numerical models, and I'm going to tell you that numerical models of climate are going to be our main tool for understanding how the climate system works. We have all this understanding of like the physics of climate that we saw in an earlier module, and radiation, and in ATS 113 you're going to see all about the 7 primitive equations, and we're going to learn more about like the forces that control the atmosphere and the processes that change the temperature of the atmosphere and so on. And that is all summarized in these numerical models. There are computer programs that contain all those rules as to how the behavior of the atmosphere works. What are the internal rules to how the atmosphere works? Now, they are going to be our main tool for understanding how the climate system works and how the climate system changes. Numerical models also give climate scientists a way to conduct experiments on the climate system. For example, let's say you want to know about how much the temperature is going to change in a world with twice as high concentrations of greenhouse gases. So one thing you could do is you set up 2 experiments using your numerical model of climate. You run one simulation of the climate with what we call control conditions. This is your control run, where like you hold the conditions with the current concentrations of carbon dioxide in the Earth's atmosphere. And then you do the experiment run, where you do the same thing, except you only change one aspect of the climate system, like you increased the amount of carbon dioxide in the atmosphere. Let's say you doubled it. So you created this experiment run. And then when you compare the output of the 2 model runs, what was a simulated climate with current carbon dioxide like, what was a simulated climate with twice as much carbon dioxide like, that is a way of conducting an experiment and is part of the scientific method. Now, the scientific method is a real theme in this course, but we are not at the present time doing more about the scientific method. We'll be doing more about that in in following modules. Numerical models of climate are actually very closely related to the numerical weather prediction models that we learned about in the previous lecture, the kind that produce forecasts of the weather. They are, in fact, very similar. They're computer programs that are based on the 7 primitive equations, and they take initial conditions and they apply the 7 primitive equations at grid points all over the world and at every level in the atmosphere and so on. And they determine the conditions of the atmosphere. They make a forecast of the conditions of the atmosphere one time step into the future, where a time step is typically on the order of a few seconds. And so these climate models work pretty much the same way that the numerical weather prediction models work, that make the kinds of forecasts that you see on TV or find on your favorite weather website or whatever. This is actually fuel for the skeptics. The skeptics actually say that for them, that's part of the reason why we shouldn't be trusting this. Because, I mean, frankly, lots of people, regardless of how they feel about climate change and stuff like that, plenty of people don't really trust the meteorologists when it comes to day-to-day forecasts. And that's not an entirely ununderstandable thing. Ununderstandable, you know what I'm saying. Everybody has that story of the forecasts that have been blown, okay? The word we use in meteorologists is bust. We've busted forecasts, where, you know, the forecast was it would be light flurries and they got 24 inches of snow, or there was supposed to be a high today in the 90s and instead it was only in the 70s or something, okay? Spectacular failures like that don't happen very often, but enough that people are understandably doubtful of numerical weather prediction and the forecasts they get from their meteorologist. In fact, if you were going to say somebody who is going to be skeptical about such a thing, about this kind of idea that we're going to be able to use numerical models to understand the climate, they could argue, well, how can scientists claim to be able to forecast the climate 100 years or so into the future when they can't even predict what the weather's going to be doing 3 days from now. Now, okay, let's be fair here. This is a bit of, shall we say, a straw man argument. You guys know what the word straw man means? I just go to cut and paste a definition here. It's when you set up a sham argument so that you can discredit it. I'm obviously going to tell you that what this skeptic is saying here is not true, and then we're going to have to figure out why and all that kind of good stuff. No individual says this, but anyway, this is sort of a straw man here. We're setting up an argument that I'm going to disprove to you, okay? But before I do that, let's take a little break. This is a fairly long lecture, and I want to break it up into little pieces. Let's just make sure we're on the same page here. Here's question 1. Our primary tool for understanding the climate system and experimenting on the climate system is our set of A, physical models, B, numerical models, C, instruments, or D, paleoclimate records. Oh, okay. Pick from one of the 4 options below this video and get a little feedback before you move on to question 2.